Okay, good afternoon, everybody. Today I want us to do something about chill operations, daily chill operations, especially on power management. Uh, what is a chiller? If somebody does not know a chiller, what do you know about a chiller? A chiller is a plant used especially for air conditioning. Air conditioning. This one we use it mostly in pharmaceutical companies where we need to regulate the temperature, relative humidity, and other activities. And this one works hand in hand with the air compressors, the boiler, which the boiler we use to generate the hot air or the steam, which is a liquid in a gas. But leaving that one aside, today we are doing a book by Michael Ogembo, which is written 9th September 2023 under the working premises of Square Pharmaceuticals, Kenya. As a chiller and cooling best practices article, today is what we are going to do under the variable speed drives. As the VSD chillers deliver energy savings and real world operation. Like to introduce it, the VSDs or the variable speed drives can cut a chiller annual energy use by 30% while maintaining operating reliably over a wide range of conditions. This is accomplished in two ways. We can do it in two ways. Which first way, where we can make an operation to an extent that the chiller do not use much of energy. We save so much on the energy. Like you can now see the energy costs as well in every part of the world. And especially in my country, where everything has gone up because of the energy. But so when we do this one as a company or as an industry, we can manage our power consumption in this manner. Like for example, I just said we will do this one in two parts. As part one, where a part load when cooling capacity can be reduced. The variable speed drives VSD chiller inherently uses less energy than a constant speed chiller whenever the compressor speeds can be reduced more closely to match the load. Number two, at low lift condition, when either the cooling tower temperatures can be reduced or chilled water supply temperature can be increased. For example, if the cooling tower water temperature is at a maximum of 28, this means if the temperature surpasses 28 degrees Celsius, the cooling tower fan will start running because the sensors will be working that at 28 degrees and above, the cooling tower fan will run to enhance the cooling. And when it is below, the cooling tower fan will not run because the sensor senses that the water is in normal condition. This one we can reduce. For example, if you can reduce it from 28 to 26 maximum and you give it allowance of positive or negative 2 degrees, when you give a positive or negative 2 degrees, it means water temperature can rise to 26, from 26 to 28 maximum, or 24 to 26 minimum. That one is lowering the cooling tower water temperature, which is being supplied to the chiller. At the same time, we can increase the chilled water supply temperature. For example, if the first setting point we have 6 degrees Celsius, what do? We increase it to 9 or to 10 degrees, giving it a positive 2 or a negative 2. This means the chiller up to 4 times more than energy can be saved in the variable speed drives chiller. And this one is can be designed to operate in these off-design conditions. And again, on the other side, holding the line on operating cost. Okay, welcome back. Let's now see the holding lines of operating costs. Manufacturers today are under continual pressure to control cost without affecting the operations or work comfort and safety. What does this one mean? This one means that, for instance, if we have a machine which operates under efficiency of 100% or 100% run throughout the day, for it to maintain its manufacturing conditions or working conditions, and for it to be on a, for the operators to be on a safety or at comfort, it must run at 100%. This means there is no power save. But so today, manufacturers are on continual pressure to control this cost without affecting these conditions, the normal working conditions and the safety of the operators, because of the energy demands. And today, even if you are going to buy an automatic vehicle, you'll find that everything is computerized, everything is minimized, fuel consumption, operation period, and whenever there is a slight mistake, there must be a reset. This means that the machines are today designed in a manner that when there is a faulty, for the safety of the operators and for the safety of the operation or work comfort or work restrictions are maintained. This is the same thing which is today done with the chillers. So in a typical water-cooled chiller plant, the chiller itself accounts for most of the energy consumption. That is why improving chiller efficiency is critical to the controlling operation cost. Like for example, if you have a UC800 chiller, which consumes over 1,000 kilowatts per hour, then you reduce even to around 10%. Now from the chiller running to 100%, it runs to up to 90, 80 or something of that sort. You find that you have reduced immensely the operational cost or the energy cost. Even so, the chillers rarely operate at their full load efficiency rating because the conditions vary accordingly. The conditions vary accordingly. Like installing the VSD on a centrifugal chiller, because this is to allow the chiller to run at a lower speed under part of load conditions, thereby yielding a higher efficiency than is typical achieved by ordinary centrifugal chillers that control part load operating with inlet vanes. Using the variable speed drives is a proven way to optimize energy utilization at full and at part load, as well as under design and off design. Like today, for example, when you operate the UC800 chiller plant, when there is no load, the chilled water pumps will be running, supplying the water, but the chiller will not run. Chiller will be at stop. This one starts at a percentage of 45 and below. At 45 and below, which means there is no load, the chiller will not run because there is no need of work. There is no need of work. And when the percentage of load increases to 51, 46, 47, the chiller will start running because now there is a sense of load. The machine can now work because there is a load. Just as I was using an example of nowadays automatic cars. When you are running at a plane, you will find that your consumption is low than when you run at the hilly places. Where when you run low, the cars will be at the same speed, but the rate of consumption is too low. When you start then inclining the plane, you will find yourself moving at a very fast speed. Or for you to know this one, you'll find even the sound increases. This means the load is increased. Similarly to the chiller plant. And because of more energy is saved in a chiller, up to 30% when you do the first two things which we said, that is either lowering the cooling tower water temperature or raising the chilled water supply, which means the chiller will not run at 100%. Okay, now a graph work, which that is my figure 1. This is figure 1. Where on the x and the y-axis, well, on the y-axis we'll be having kilowatt ton, that's 0.0, 0.1 to 0.8. Then on the x-axis we'll be having load, that load efficiency. There's an entering condensed water temperature. This one entering the entering condensed water temperature. This is from the cooling tower. What do we do? Like, let's start from 45 degrees, or 45 Faradays. That is 7 degrees of entering condensed water. The chiller will be running at 40%. This means the temperature is reached to a point that now there is no big load. There is no load total. At 45 or 40%, there is no load. That means the chilled water pumps will be running daily, will be running on hourly, because there is no load for the chiller. That means the set point of the chilled water temperature is higher than that, which means when you force the chiller to run, it will be struggling to reach the point. The chiller will be straining, and when the chiller is straining, I hope you understand, when you force even yourself to eat something you cannot eat, you will be disgusted and you cannot continue. Then at 55 Faradays or 12 degrees of entering condensed water temperature, the chiller will now start rising to 60, not 60, around 50 something, 51, 52 there at 12 degrees. Then at 65 Faradays, that's 18 degrees Celsius, entering condensed water temperature is at 18. The efficiency or the load increases softly. At the same time, at 75 Faradays, that's 23 degrees Celsius to 29 degrees Celsius, that's 75 to 85 Faradays, the chiller will run at more than 66%. But from 18 degrees to 23 degrees, the chiller will be running at a range of 60 to 66%. Compared to where we have a 29 to 23, that is the entering condensed water temperature, where we have 29 to 23, the lift load is a bit high, which means the chiller will be running above 66%. That one is where we'll start to see the orange line. The orange line on the yellow means the load is now increasing to 85. We'll have reduced 15%. But when it is below 29, we'll be having a reduction of 16% and above. This is a good working condition for a chiller, and this one leads to a lot of energy save. That's a 30% save on energy. The two variable in energy savings. Example two variable in energy savings. Of course, the cooling load capacity is a factor affecting the chiller energy consumption. The cooling load energy. The cooling load capacity affects the chiller energy consumption. Like, for example, if entering condensed water temperature is at 30% and I need chilled water temperature to be at 9 degrees or at 6 degrees, it means the chiller will strain. It will be 100% workload than when I have 18 condensed water temperature entering the chiller and 9. That means we'll be running at a half the load that we had in the first one. Of course, as shown in the graph, when the chiller at a constant entering condenser water temperature can reduce load by 50%. Its efficiency kilowatt ton at new conditions improves by 15%. Then the load reducing is possible because the number of the days when full capacity is required are few, according to environmental protection agencies. Then chiller spends most of their operating times at 40 to 70% load under conditions that are often considerably different from the standard conditions. But this one will also depend on the company regulations. Like a pharmaceutical company where you work, there's pharmaceuticals. There are some conditions which require a fast cooling or below 25 degrees for medicinal production and medicinal storage and processing, blistering. But on the blistering area, we don't use chiller most, but we use the compressed air. This one will not affect so much the chiller. But now production might affect the chiller performance because of the conditions of the relative humidity and the conditions of the temperature or the chilled water temperature which is needed in the room. At the same time, we have to know the stress temperature period, the stress temperature period of the medicines which are produced. This is most likely, like for example, if my storage temperature should be 25 degrees and the condition where I am working is very hard to have that 25 degrees, what should I do? So this is what should I do? This is the stress period, the stress temperature. What temperature should I make so that, for example, if I move the medicines from Nairobi, which in most occasions the temperature is 25 degrees on the environmental temperature, then I move to Isiolo or Garissa, where the temperature is over 29, reaching 30, and the medicines which will be stored at 25 degrees Celsius. How will I manage this temperature? So this is where the load can be now not very easy to balance the load, but when calibrated successfully, there is opportunity for the survival of the medicines. And as you understand, whenever you mess with the medicine, you mess with the people's life. Medicine is only a medicine when the condition is met, but it comes to be a poison when the conditions is not met. And I hope this one is the best for today. So let's meet on the other class. When there is a question, just post to my mail. On the chill operation, post to my mail, mycorpogambo128@gmail.com on the chill operations. And in energy controller. And again, for more information, next class will be handling something about ETP, industrial, or IETP, industrial effluent treatment plant. How do we treat industrial effluents? And treatment is not just done because we know how to do treatment. Treatment is done based on the processing company. What do your company process? What do my company manufacture? Like, I cannot compare a sugarcane company effluents with the pharmaceutical company effluents or cement company effluents. These are very different industries, because you will find that in most occasions pharmaceutical companies use chemical daily basis. So that one will depend. So next class we'll be talking about ETP, or industrial effluent treatment plant management. Thank you. Have a nice time. My name is Michael Ogembo, a utility engineer in Square Pharmaceuticals, Kenya. Bye.